Welcome friends. So we are discussing module 9 of network theory, application of Laplace transform to solve transient response of electrical network. So with continuation to the previous session, now let us discuss the transient response of series RL circuit. Transient response of series RL circuit. Okay, so we have already solved this network using differential equation approach. Now we shall see our alternative approach. So we have a series RL circuit, RL network with a DC excitation V. We have a series, initially we have a switch. Okay, this is a switch. Initially it is open like this. Now it is made close at t is equal to 0. Now it is made closed at t is equal to 0. So when it was open like this, so we have a DC source at the input side V. We have a RL. So since it is open like this, so no current should be flowing. So we can write I0 minus that should be equal to 0. So as the moment it is closed, the switch is closed at t is equal to 0. With that, so I0 plus will be also 0, because we have explained, or we have understood that through inductor there should not be any instantaneous current change. So IL0 minus should be equal to IL0 plus. That is our initial condition for this. So now we have our KVL equation. So it is well known, V is equal to R into IT plus L into dIdt. Now on this equation, on this KVL equation, if we apply Laplace transform, so V will become V by S. So V is equal to R into IT plus L into dIt dt. So with applying Laplace transformation, this V is a constant voltage source, so it will become V by S. So R will be as it is. So now IT, it is the current as a function of time, so it will become IS plus L. Now you follow the derivative rule, just we have done in the previous session. So it will be S into IS minus I0 plus. So it is a derivative rule. Now just we have seen, we have checked our, from the initial condition we can say I0 plus, that is it, that will be equal to 0. So from there we can write V by S, that will be equal to, now if you take IS common, so it will be R plus S into L. So with that, IS should be equal to V by S into S plus R by L, and in the numerator we will have a V by L. Okay, so this is a IS. Now, or if we again, so if we write with the continuation, if IS is like this, so V by L is constant, so we should not disturb this. So if this term can be written as 1 by S minus 1 by S plus R by L. So let us check. So from there, what is coming actually? If we solve, what is coming? Only we are evaluating only this much, right? So LCM is S into S plus R by L. So if you take, so it will be S plus R by L minus S. So SS cancel, so it will be R by L. So you need to multiply it with a L by R to make it equal to 1. So you see here it is 1, right? Here it is 1. If you take LCM, then in the numerator it should be 1. So if you take LCM of this, then it should be S plus RL minus S. So SS cancel. So in the numerator we have R by L. So to make it 1, so we must multiply it with a L by R, right? So we are multiplying it with a L by R into L by R. So that is exactly this thing is done here. So which is nothing but IS, or IS that will be is equal to this L, and this L gets cancelled. So it will be V by R into 1 by S minus 1 by S plus RL. So you will now apply, or you will directly write the KVL or inverse Laplace transform. So IS inverse Laplace will be IT. So V by R is kept constant here. Now what is 1 by S inverse? So if we have a unit step of 1, then its Laplace transform will be 1 by S. So vice versa, if we have 1 by S, then its inverse Laplace transform will be 1. So in time domain 1 by S is simply 1. Minus, now 1 by S, it will be 1, but again you see it is shifted by an amount of R by L in the frequency domain, then it must be multiplied with the time domain by a factor of R by L into T. So with that, our final expression is like that. So IT becomes T by R into 1 minus e to the power minus T over tau, where tau is L by R. So we will have exactly the same expression. We solved exactly this expression in the time domain analysis. What is the IT? IT is equal to V by R into 1 minus e to the power T by tau. So we have solved exactly this thing. And from there, if you are interested, you can solve from here what will be VRT and what will be VLT. You will get same expressions. Now moving on. We have series RC circuit. So we have this KVL equation, V is equal to so let me write it down. So what will be the KVL equation for series RC circuit? Series RC circuit. So we have V as a input voltage, then we have R into IT, that is the voltage drop across the resistor, and voltage drop across the capacitor, you know, 1 by C integration 0 to T IT dt. Now with that, if we apply Laplace transform on this equation, V will become V by S because it is a constant voltage source. R into IT will become R into IS in the Laplace domain. 1 by C, it is a constant. Now if you follow the integration rule, integration 0 to T IT dt, it will be simply IS by S. It will be simply IS by S if you follow the integration rule. So with that, V by S, that is equal to V by S, that will be is equal to, now if you take Is common, so it will be R plus 1 by Cs, right? 1 by Cs. So from there, if you have Is, so it will be V by S in the numerator, and then in the denominator we have R plus 1 by Sc. So V by S in the numerator. Now in the denominator, if you take Sc common, so it will be 1 plus RCS, 1 plus RCS. So it will be actually this SS cancels. So this S and S cancel, so it will be V into E over 1 plus RC into S. So again, if you take RC common from here, so it will be becoming S plus 1 by RC. Okay, so this final expression of Is becomes V by R into 1 by S plus 1 by RC. There we can write now what will be the inverse Laplace transform. What is with the inverse Laplace transform IT? That will be is equal to V by R into e to the power minus t by tau, where tau is equal to RC seconds. So exactly this equation we have derived in case of a series RC circuit. Exactly this equation we have derived in case of a series RC circuit. So whatever be the method, the results remains the same as we can see. So now from here you can evaluate what will be the VRT and VCT. VRT and VCT we can evaluate, right? So lastly we have series RLC circuit. So we have similar KVL equation that will be, that is V is equal to RIT plus L into DIT dt plus 1 by C integration 0 to T IT dt. Okay, so if you apply Laplace transform, it will become V by S, then R into IT becomes R into IS plus SLIS minus plus 1 by CS into IS. We assume 0 initial condition for simplicity. That means 0 initial condition. What does it mean? Current flowing through the inductor is 0 and voltage across the capacitor will be also 0. That is called 0 initial condition. So from there, if you solve sorry, it should be, no, okay, it is okay. So from there, so if you solve actually, so V by S, so it should be, if you take Is common, then inside the square bracket it should be R plus SL plus 1 by SC. So with that, Is common, so in the denominator it should be 1 by Cs. So first term will be RCS plus then LC square plus 1. So this S and this S gets cancelled. So with that we are getting Is will be equal to V by, now if you take LC common outside, so this will be S square plus RC by LCS plus 1 by LC. So with that, V by LC with S square plus R by L S plus 1 by LC, this is the expression of Is. Now if we substitute, or if you think that S square plus R by Ls plus 1 by Lc, that is equal to 0. So the root of this equation is given in this equation. Now the solution of this equation Is is totally dependent on the roots of this equation. Actually this equation, that denominator, that this quadratic equation is called characteristic equation. It is called actually characteristic equation. Characteristic equation. So whether this problem or this IT, if we plot in the x-axis t and the y-axis it, so we have already defined three types of responses. First we have defined underdamped response. It will take closely this shape. Then we have also defined, this is called underdamped response, right? Underdamped response. Then we have also mentioned that this type of waveform or this type of response, it is called critically damped response. Critically damped. Also we have seen, or we have observed this kind of response which is called overdamped response. So it is totally dependent on the roots of the characteristic equation. Okay, the roots of the characteristic equation. So if this R by 2L, we have mentioned that R by 2L whole square, if it is a greater than 1 by LC, if it is a greater than 1 by LC, then this response is called overdamped. Damped. We have already mentioned. So if it is equal, then it is called actually critically damped, right? It is called critically damped. And if it is a less than 1 by LC, then it is called underdamped. So whatever be the value, it will perform accordingly, underdamped, overdamped or critically damped. So it will totally depend on the roots of this quadratic equation, or it is called characteristic equation. So this is actually transient response of series RLC circuit. So depending on the value of RL and C, our network will observe respective responses, whether it is a underdamped, critically damped, or overdamped response. Okay. So with this, we have seen that we have obtained same expression of current in case of series RL circuit as well as series RC circuit as well as series RLC circuit using both the techniques. Okay. So we are ending here. Now from the next session we shall solve some numerical problem with some with this Laplace transform technique. Thank you.